and the FOSDEM. But my job is a little bit different because usually I work on third-party hypervisors. What I do is that I support Linux as a guest on other hypervisors than KVM. Mainly, I work on hypervisors like Zen, Hyper-V, sometimes on VMware. So the idea of this talk was influenced by last year's KVM forum talk by Jim Maxson from Google. In his talk, Jim, is he here in the room? No. Okay, so I can talk whatever I want. Well, so he was talking about nesting KVM on KVM. And while this is really important and interesting, in his talk he was mainly describing which optimizations we can do for KVM as level 0 hypervisor. And when we run other hypervisors being nested, we don't have such options, especially when we run on something proprietary and even like Hyper-V. But can we still do something in Linux to be a good guess? And actually, are we a good level 1 hypervisor or not? So this is basically the idea of this talk. So now the setup. So what's the setup I'm going to be talking about in this talk? So basically, we have Hyper-V installed on their hardware. And as you know, Hyper-V is like Microsoft proprietary hypervisor. It's a type 0 hypervisor, or top 1 hypervisor, which is split between the hypervisor itself and the management partition. And the management partition for Hyper-V is always Windows, for now, but who knows, right? So what we're going to do is we'll be running Linux in the VM, but inside this we will run KVM and we'll try to run level 0 guests. Only Linux for now, so I haven't tried Windows, so those kind of possible. Why is it important and why would you actually care, why would you want to try that? Well, there is no simple answer for that, but my answer would be that it's mainly because of Azure and some other private deployment of Hyper-V. So it may happen to you that your customer, for example, is moving to Asia, right? And you have no choice. So you have to move your workload or containers or whatever you run to this hypervisor. Because of some non-technical reasons sometimes, like price was good on Asia, for example. So what you can do with this second level virtual machine? Well, first you can try splitting big instances into chunks. For example, like M128 instance in Azure, if you know, it has 128 CPUs, 4 terabytes of memory. That's a pretty big instance. So sometimes you may want to actually divide it into several parts and treat them separately. You may be interested in running secure containers. Stuff like Intel player containers, Kata containers, Beer, which you just heard about from Fabian. So you may actually want to run virtual machines there on this cloud. And for that you definitely need this virtualization there. So as well you can just want to move the whole workload that you have or do some testing and debugging there. It's also possible. So, nesting in Hyper-V. It's relatively new. They only added it in 2016, and they were mainly targeting running Hyper-V and Hyper-V. Why did they do that? So, at least what they told me is that their main driver was because in this 2016 family of this Windows as proprietary even, they added some security features which are virtualization based. And if you want to use this feature and you are running a virtual machine, that means that you will be running nesting. So if you have just a single Windows setup, Windows 10, Windows 2016, nesting is not enabled there by default. You will run a virtual machine and KVM won't load there. It will tell you, sorry, no hardware support for that. There's no Linux extension for that. So you have to enable it. And after we do that, it all starts working. At least that's the expectation. So you can run KVM there, you can machine there, they can basically do whatever you do nowadays with KVM and the whole stack on bare hardware. So, great, right? Are we done? Well, in case you're not using it for testing purposes, you may be interested in how well it actually performs, right? Especially if you want to run like a container. You don't want to have significantly lower performance of the container compared to like level 1. So what I was interested in when I started working on this like several months ago was like, okay, cool, it works, but does it really perform? So I started doing several benchmarks, trying to look at various aspects of such nesting. And the thing is really that every particular workload requires taking care of, because different workloads have different implications when you run them in virtualized environments in the first place, but in nesting it's even more complicated. So, first example, I hope you can see there, is like a classical example of how would you test your virtualization in general. I will try to explain later why, but this example is a simple thing. It's just a type CPU ID loop. I hope that everybody in this room knows that, but like RDTST returns this like cycle count from your CPU. It's just a counter. It's a single assembly instruction. You run it, you get the counter. CPU ID is another instruction which, like this particular one, returns this like main CPU feature, I guess. And we try to see how fast this works, right? Very simple loop. So, the result. If you run this from bare metal, something like Skylake processor, you will get like 180 cycles. Level 1, and here level 1, I mean, we run Linux on Hyper-V, not Linux on KVM. You will get like 1,350 cycles. With KVM, it's very, very similar. I got like 1,200 in like less than this count. But if you run a virtualized guest on Hyper-V, you will see something like that. That's kind of a lot. I mean, more cycles is spent on each instruction worth of performance, right? So, is it bad? It is. But can we make it better, actually? Right? Why is it better? And for that, to actually like understand that, you need to know how virtualization on Intel works in general. And I'm sorry, I will only be talking about like Intel virtualization today. AMD is somewhat similar. With ARM, it's like significantly different, so I won't be getting into that. We don't have Hyper-V for ARM publicly released yet. So we know that Microsoft claims that they have it internally, they run it internally, but nobody outside of Microsoft knows, and I didn't see it either. So, how does virtualization work on Intel? So your hypervisor, it's like this, it doesn't matter if it's like KVM or Hyper-V, any hypervisor on x86 will do the same. So you prepare a special area which describes your guest, and there is like one page of memory, 4 kilobytes. And this is like a special area in memory, but which you cannot like edit directly. You need to like use special CPU instructions to access it. And you describe your guest, where is the starting point, like what are all different things, like all these x86 features you have. And when you create this memory, it describes your guest, you basically run it. And after that, your guest runs on CPU uninterrupted. You don't do anything from the hypervisor. So the hypervisor is not involved in that case. It's only when your guest will do something special which requires some attention from the hypervisor, which cannot be done. You will turn back into the hypervisor. Hypervisor is supposed to handle the trap and receive the guest. And that's how it works. Like, we wait till the traps, we handle, we resume. With like several guests, we sometimes like schedule them out, schedule them in. It's like a little bit more complicated, but in a nutshell, it's like that. So this is like the first level of virtualization, very simple. Okay, so how would you think message virtualization works? If you didn't know anything about it, if you haven't read Intel's manual, you might think that level 1 hypervisor just does the same, right? It prepares this area for its level 2 guest and it runs it. And when something is happening in level 2 guest, we will jump into level 1 hypervisor, right? Handle the fault, resume level 2, and continue executing. But it's not how it is. From level 1 hypervisor's point of view, and yeah, really, speaking about messages is a little bit confusing, and I can even confuse myself, saying this level 1, level 2, it's really not easy. I'm trying. So, how does it work? So, level 1 hypervisor thinks that it's basically like the only hypervisor in the system. So, it prepares the area. But when it runs the area, it cannot be run. It first needs to be merged with the idea of what level 0 hypervisor thinks about level 1 hypervisor. Because like level 1 hypervisor may already have some restrictions. And we cannot prepare a guest which will have less restrictions, right? So we need to merge these two ideas. So when we run, we actually go to level 1 hypervisor. Level 1 hypervisor analyzes the state which we just created, merges it with his ideas of how it needs to be run, and then it runs it in parallel to level 1 hypervisor. So it's not really on top of level 1, it's actually like in parallel. But the interesting thing here is what happens when we trap. Like, we execute this CPID instruction, right? CPID instructions by Intel manual, they're always trapped. We get in at level 0 first. That's the only real hypervisor in the system. And level 0 looks at the exit, like, oh, the exit is probably not for me, or I'm not going to handle it. So you can pass execution flow to level 1 hypervisor. And level 1 hypervisor will think, oh, our level 2 guest just trapped. But it's not like that. It didn't just trap. It's like the execution flow is coming from level 0. And it's significantly slower, of course. Especially when level 1 hypervisor tries to like edit the state. It tries to do these special commands like vim read, vim write. You're familiar with them probably. And by default, all these commands trap into level 0 hypervisor. So Intel came with a feature like 3 years ago, which is called like shadowing CS. So level 1 0 hypervisor can actually load like a special this special area for level 1 hypervisor, which won't be executed, but level 1 can access it directly. So no VMXs, and make it pretty faster. But still, when we try to run our level 2, we still need to tap into level 0. Level 0 needs to analyze all the states, merge it with this idea, and run level 2. And that's how it works in Intel. So, back to our question, can we make it better? Well, we cannot make it as good as exit from level 1 because of these architectural limitations. We will always be trapping into level 0. Level 0 will always be performing some work for us, then merging these ideas and resuming the guest, and each exit will cost us significantly more than what it costs us on level 1. But we can still do better, and Microsoft folks in their specs, they have publicly available spec. You can download it. It's like PDF which describes all the features I'm talking about. So they created a feature called like enlightened in CS. The feature means that level 0 with level 1 will communicate through a well-defined structure and memory. So level 1 suddenly becomes aware, oh, I'm running nested, so I can try to help level 0 hypervisor. I will try to tell it what I actually changed in the structure. So we don't need to actually analyze the whole state, because if level 1 was getting something in the structure which we have no access to, we don't know, right? So they created this like PV protocol for the interaction, and the PV protocol is significantly faster. So There is actually on the mailing list. It's still in works, but I would expect it to get merged into 417. Like not this kernel, but the next one. Because this merge window is already open and we are still working on this one. So, the result. Well, we go down to somewhat less than 9,000. And if you remember what I showed you, we had like 40,000 before. So this is actually a significant speed up. It's really good. So, next benchmark. So that was the benchmark with CPU ID. Let's try doing one simple thing. Let's write the type individually, trying to figure out what's the time right now, right? And while it may seem very synthetic, right, like you would do that in this program, it actually is being used. If you have like an Apache server running and it's trying to output something to its logs, it will try to timestamp each entry in the log. So it needs to get the time stamp. So it will actually be doing something very, very similar to that, reading the time from the system. So, simple use case, let's try to see how well it performs. Okay. Again, bare metal, 55 cycles, so it's pretty fast. You run it, you get it instantly. In level 0 or level 1, it's not significantly different. 55 or 70 CPU cycles, it's nearly the same. But in level 2, you will get something like this. And this is post this spectrum meltdown fix. Before that, we had 300. So that's it. Yeah, I had to redo this test for this talk multiple times because kernel was changing so fast that I didn't want to show you this scale number. Like I had 300 sitting here like a month ago, but then I decided like what's the point in showing you 300? So it's 1,500. Well, that's not gonna perform well to make it, and you're correct. So what next? I mean, it doesn't perform, and we need to figure out why. You may have a valid idea that something with our clock source is wrong, right? We probably have a better one somewhere. So what do we have? If you check on level 1, we get like so-called like TSC page clock source from Hyper-V. And on level 2, we get KVM clock. And if you go read the guidelines, like how do I tune my system to perform on hypervisors, you will see that these are actually good clock sources for both of them. So for Hyper-V, it will be said that use Hyper-V clock source TSC page. For KVM clock, they will tell you, for KVM, they will tell you KVM clock is probably what you want to use on KVM. And they both perform very well, usually. But for some reason, they don't perform very well here. Why? Well, at this point you have to use some tools like Perl to figure out why, or even go and read the code. So I did. And turns out that currently KVM only treats TSC clock source as the valid clock source to make its guest clock source stable. Well, what does it mean? It means that in case you use something different from TSC in your host, virtualization host, which is L1 in our case, stable clock source won't get passed to your level 2 guest. And then comes the difference. When your clock source is not stable, you can't use VDSO method in kernel. And VDSO means that you are not doing a syscall. You are not doing a syscall, you are reading it mostly natively. And that explains these like 753 cycles which you get. If you do a syscall, you get what you get. And post Spectre, when we have to actually switch to tables on that, 1,500 is no surprise. So can we actually like teach KVM and tell it that Hyper-V clock source in the TSC page is like a very good clock source? Well, yes we can. And we do that, simple patch, it all starts working, very well. I will show you numbers later. But we get an issue. Imagine you want to migrate your level 1 with all its level 2 guests inside. And you migrate. So what happens when you do that? You may want to migrate to a different CPU which has different TSC frequencies. So like CPU with different frequencies. Okay, you can do that. And what will happen? What is the CSC page called source and why do we need it? The CSC page called source is basically just a shared memory page with 2 integers, which tells us that when we read TSC from the hardware, we need to multiply it and add some offset. So we can actually basically like scale it and add some offset to it. So when we actually migrate, the hypervisor will update this page for us. And when we read it next time, the reading will be correct still. So we won't see it jump. We won't see it like speeding up or slowing down. We will still be seeing the same code source we saw before. And that's what we actually need in there. Because if we ever like go down, your user space will go back, your user space will definitely decay. If your frequency will change, then you may measure time your program is incorrectly. So we actually need that. And this happens. Hypervisor does that automatically for us. No need to worry. But what happens to level 2 guests? In level 2 guests, we have more or less the same protocol, which is called like PV clock or KVM clock source, if you look from the clock source side, which is supposed to do the same. Like when we migrate guests which run on KVM, KVM will update values there, so the reading will still be correct. But nobody actually told KVM that we just migrated. Because it's not a virtualized guest, so it's not aware of migrations. We need to somehow tell it that please stop your guest and go update all the pages before you are able to execute them again. So the readings will still be correct. And we need to do this exactly when we migrate. So can we do that? Yes, we can. In the spec, you can find so-called real-life feature, where things work. So you can ask your hypervisor, Hyper-V, to send you an interrupt when you migrate. And you can ask it to emulate all TSC access before you manage to update all the pages. And we did that. And after that, these are the numbers we get. So, as you can see, this issue here goes away completely. So, such workloads will run in level 2 with exactly the same speed as, basically exactly the same speed that they're running in level 1. So, they're not any worse. Okay, so these were some micro benchmarks and some synthetic tests you may think, but how does it affect real workloads, and shall you actually use it nowadays? Shall you wait till it gets merged into the kernel? Well, so I took basically 2 bigger workloads and to do my measurement. And the first one was iPro. If you know that iPro is like a performance benchmark for networking, it uses like big packets, so it's not something like NFV with like small packets, not something like DK. So we just take the code channel and we are trying to like saturate the code. We can send like traffic to parallel and we look how well it performs. So the hardware setup is somewhat important here. But like pretty powerful. We have like 40G network card, one server with 2 nodes, and as it's like well enough to connect X3 card, we can actually do SRIOV. SRIOV in Hyper-V is kind of special because it only supports a few network cards nowadays. So it's like with Mellanox, some Intel, and I think that's it. So, but I was lucky to find one which is actually supported. And when we run our level 2 guest, I was running like vanilla Fedora kernel after with this meltdown factor fixes unmodified. And the question is, how do we connect level 2 network to the real network? And with Hyper-V, we don't actually have many options. Because even with virtual functions, we can do some sort of a bridging there because we can't have more than one address there initially. So we can put it in like promiscuous mode, like here in level 0 won't allow us to. So I was doing what like libvirt does by default. It creates like a vhost. The only thing I changed was I changed the number of using vhost to make it like 2. And using that constant device. So, okay, we have like big guess for level 1, we have like 1 new node for level 2, and we will run Hyper. So, how well that is before? Yes. So, these are the numbers. As you know, if you run it in level 1, you need like 4 parallel streams to saturate this 40 gigabit network card. With level 2, it's worse, but it's not like in these synthetic examples when they're 10 times slower, right? So, especially when we add this legend to LCS support, we are basically able to saturate the network adapter 2. We only need like more streams. And it gives us an advantage compared to using like normal DLCS and pretending we don't know anything about Hyper-V and graphs. But as you can see, the difference is not that big. So for this real Hyper benchmark, they're actually doing good even today. So you can go ahead and try using it. And what you can actually play with how to tune this setup. I'm not going to pretend that that was like the perfect setup. You can probably make it better, of course. So you can use like CPU pinning in L2, especially, or in L1, especially if you have like multiple NUMA nodes. So you may make your level 2 guess nowhere where, or you may pin it to a single NUMA node, and that's what I did. Like 8 to 2016 and pin them on one NUMA node. You have multiple settings to play with in vhost, and there are like multiple presentations and talks and everything on how to do it properly. I'm definitely not an expert. I played with them a little bit and turned out that like with GPUs we get the best result. Not sure why. And you can actually like see your hardware, but like I found out that like Mellanox is doing a great job by default. It will create as many queues as we have CPUs in one NUMA node and will pin them accordingly by default. So I didn't have to do any changes there. Okay, so another big part is going to be almost the same, but just in case you're not that lucky and you won't find a network card which you can use as thorough DBs in Hyper-V, you have to use emulated device, so-called like VMBus or Netlist you may be familiar with. And other than that, the setup is like exactly the same. So I just like turn SRIV off and try to see the difference. And you will see something like that. So yeah, this is level 1. Instead of like 4, you have to use like 5 streams, but we can still saturate this device easily. With level 2, it becomes more complicated, and we're actually worse. We're only like reaching 30 gigabits. And our enlightened PMCS doesn't actually help us a lot, as you can see. So why does it happen? Well, it's probably because we have too many copies of the same data. L2 uses vhost and uses this virtual map and copies it to the host. The host copies it to VM bus ring. VM bus ring is being observed by Windows, which takes this packet and copies it to the real queue of the network card. So we are not able to reach better than touch. That's the price to pay. Again, here you can also do stuff like CPU pin and vhost technique, but we have one additional complication. If you use Hyper-V emulated devices in the kernel nowadays, they use like VM bus. And instead of real like interrupts, they use so-called channels. And these channels, they are being distributed automatically. Unlike an IRQ, which you can do something like run an IRQ balance and it will try to put them on different CPUs. This thing the kernel driver will kind of distribute them randomly, and it will stay like that. You cannot change the assignment. So what you can do, you can try like pinning your guest to like different CPUs, for example, which is not really like a practical advice, because next time you boot, you may get a different distribution here, which you can only observe. So, and in Hyper-V, there is no way to reassign channels. There is no such line. So we cannot make it supported in the kernel for now. Maybe like Microsoft hopes to see that and give us an option for that, but so far we are not aware of it. At least it's not in the public spec. What you can play with, you can try changing the number of channels on this net receiver. It's like a side effect of this change. The network adapter goes away and comes back, and you will have a different distribution. So if you don't like to get change number of channels, you will get more likely with that. That's like a hackish approach. Okay, so yes, so the last benchmark I did was a kernel view. That's so-called like a bench, but I wasn't running the script itself, I just did the build. And to compare like apples with apples, I had to like reboot my level 1 into the same kernel as L2 was running. So when it was not running level 2, it was running stock Fedora kernel. When it was running L2, I was doing tests on like RC8 plus my delighted VMCS and this scope source. So what do? We just build kernel in like 8 strings, do some all yes config and yes, and we build the kernel. So how well does it perform? You know, if you try, you will see something like that. As you can see, the numbers are very close, actually. And our enlightenment said don't even help in this case. Actually make things a bit worse. So why is that? Well, the answer is that when you run such workload, which is CPU intensive, we don't do many VMXs, as I explained to you in the beginning. We are basically sitting on the same CPU and doing some like computations. So as we expect, the speed is the same, right? We are still on the same CPU with the same instruction set. And you don't actually need to optimize anything if your workload is only like CPU intensive. Oh yeah, I have to mention that I was running this on in memory, so no real hard drive was used, so the kernel was used on KVM. So if you mine Bitcoin, it doesn't really matter where. If you use your CPU for mining Bitcoin, why would you do that? You can do it in level 2 equally good or equally bad in level 1. So, what else? What's left if you read the spec? We have a couple more features which we are not implementing in Linux yet. And first is enlightened MSR group time. And it's a thing where you can tell level 0 hypervisor, but yeah, I have to probably describe it like that, but when you run the virtualized guest, you can create a page with all this bits for all MSRs. MSR is like model specific reader register, you CPU, you read it and you get some result. And you can actually tell the CPU when you want to have the VMX, when your guest reads this MSR or when it writes to this MSR. And we have like a memory page. And again, the problem is exactly the same we had with like normal VMCS, that when our level 1 hypervisor edits the structure, we don't really know what was changed there. So we have to go through the whole page and check all the bits in this page to see if something was changed. Maybe nothing even was changed in there, but we don't know. So they again introduced the protocol that when you can tell your hypervisor, your level 0 hypervisor, meaning Hyper-V, when you can tell it if something was actually changed in this page, and it really needs to examine it before it resumes executing your guess. And it's supposed to speed things up a little bit, but we don't have this yet. The other interesting thing is the PVTOB flash. And it's interesting even without this L2 guess. As you may know that we sometimes need to flash TOB, for example. Right now we switch from like kernel pages to user space pages or in the other direction, and we sometimes want to flash TOB so we won't get stale entries there. And how is it done in x86? In x86, we have no single command, just invalidate TLB on all CPUs you have. If you want to invalidate your TLB on other CPUs, you have to send an interrupt there, basically like an IPI. The processor will catch the IPI and invalidate its own TLB. So virtualized guests can do exactly the same. They can send RPIs to other virtual CPUs and they will execute and flash their buttons. But the problem is that some of their vCPUs may not be scheduled at this point. Some other guests may be running there. So we send an interrupt there and it's pending. Because the CPU is not executed, like we will execute it later. Moreover, the CPU which actually sends these APIs, it's waiting for the job to be done. So it all becomes significantly slower when you haven't overcommitted guests, when you have more than one vCPU per physical CPU. So KVM folks, they came up with a PV protocol, that's their solution to all issues, come up with a PV protocol when hardware doesn't perform. And they introduced a code like PVTOB flash. You're basically executing a hypercall instead of sending RPIs to all CPUs, and your hypervisor will see if it's some different CPU which sits there, not from your guest. You don't even need to invalidate TLB there, because the side effect of switching vCPUs there is the TLB flash. So basically it does nothing for these CPUs. And on CPUs which are actually scheduled, actually does the TLB flash. And we, like this year, several kernel releases ago, I forgot the number, we add the support for this protocol in Linux. So when you run Linux on Hyper-V, you can benefit from this VTOB flash protocol. The feature they have, and which I listed here, is that they have direct flash for level 2 guests. Because when you are running nested, the probability that your virtual CPU is actually being executed at this time is even lower than with V1, right? You may have several level 1 guests, and in each level 1 you may have several level 2 guests, so they just get a tiny, tiny portion of real CPU. And they provide an option to do this TLB flash directly from L2 guests. They will just go into level 0. Level 0 will examine which virtual CPUs of these guests are currently scheduled and do TLB flash accordingly. So this is also supposed to bring some performance improvement, on the virtualized level 2 guests. But work hasn't started yet. So if you're interested, join. Or just follow. I'll try to get to sooner or later. And that's it, guys. So if you have any questions, Yes, you can. The question was, what's needed to start nested guests on Azure? And the answer is that they have certain instance types which support it and certain which don't. Azure is made of different hyper-reversions. So if you look at it, that new instance types which run in 2016, they have a name. So I know for sure that this is the biggest M128 supports it. I think that the instances version 3 support that, and maybe E version 3, something like that. I'm not sure about certain instance types support that. Yeah, so drop me an email. I have this somewhere written. I asked Microsoft directly, and I have a reply to this question. But you may just try with KVM module load, just like module of KVM in tab. If it doesn't tell you that, oh, no hardware support, then it's support. If it does tell you that, sorry, it's not support, then you have to try another instance type. You have no pressure, enable or disable. They will do it on their own for you. Another question? Yeah, please.
How does the usual nested perform compared with traditional nested, like KVM on KVM?
Yeah, the question was how does it compare with running KVM on KVM? And the answer is that when we implement these KV features like Enlightened TMCS, we perform significantly better than KVM on KVM. KVM can really run faster. In particular, Paolo told me that before Spectrum meltdown, he was able to reach something like 13,000 CPU cycles on nested VMX. That was like the best setup he had. With my series, yeah, I saw 7,500, so like half. We have a huge room for optimization inside KVM being level 0 hypervisor. And we may actually think about bringing this feature to KVM one way or another. Yeah, so I still have a question about, sorry, the time is up, so just approach me in advance. So, thank you again.